So one of the best ways to understand twinning is to look at the twinning operation as it applies to the FCC structure. I have an FCC crystal here, there's a 1-1-1 plane here, there's a 1-1-1 plane there, and 1-1-1 plane there. These are the close packed planes, 1-1-1. As you will realize or probably know, that if you're talking about dislocation slip in an FCC structure, it takes place by shearing on one plane. Let's take this middle plane. We shear it in one direction, which is the partial. It's a 1-1-2 partial, but we can't keep going in that direction because this atom, or this row of atoms, is blocked by another set of atoms directly in front of it if you wanted to keep going in the same direction. But you can add a different shear, and that brings us back into perfect registry with the crystal. So that's a perfect shear dislocation of a 1-1-0, half 1-1-0 displacement. And then there's another one, and you can continue if you want. But what you have is a shear on a plane. Now, twinning is a bulk shear, in which case you have shear on multiple planes. Now, as I said, if you're trying to shear in one plane, if you only move one partial on where the atom can glide, there's only a limited amount of shear that's possible in one direction. But on multiple planes, you can keep shearing in the same direction on each successive plane. So we'll start here. We'll start here where the twinning plane is call this a 1-1-1 and call this 1-1-bar-1. And if I apply a twin shear, we move one layer over by one partial, the next layer over by a partial, the next layer over by a partial, the next layer over by a partial, and the next layer over by a partial. In which case, that then gives me my shear displacement. And I can do that and therefore get a substantial shear in a bulk. Now the other issue about twinning in FCC, which is kind of nice because you don't have it in HCP, is that when you perform the twinning operation, at the end of the twinning operation, certainly on the 1-1-1 plane, at the end of the twinning operation, I think for any other plane as well, the crystal is in perfect registry. So to demonstrate that, let's look at this plane here, which is a 1-1-1 plane. This is my twinning plane. The base here is my twinning plane where I'm shearing. And I look at this plane, and let's perform the twinning operation in this direction and move each layer over by one partial. What's happened? I still have my FCC plane, my 1-1-1 close pack plane, but it's now oriented in this direction, whereas before the twinning operation it was oriented in this direction. So we've gone from this to this. This is what's known as the second undistorted plane. The first undistorted plane is the basal plane. But in fact, in FCCs, all of the planes are undistorted, because when you perform that twinning operation, this particular twinning operation, which is involves a shear of a 6-1-1-bar-2 partial, then you end up where the crystal is within the twin is in perfect registry. However, at the plane of at the boundary of the twin, we have a stacking fault because we have an ABA stacking instead of ABC stacking. So we have a stacking fault at this point.